All right, so one of the things that I need to mention for the APC is rotational inertia. Now, we kind of talked about it, We've kind of talked about it in the one class, but now I have to go into a little bit more detail about this. Now, there are two ways that you can determine the rotational inertia. First off, you should be aware of these equations. The rotational inertia of a rod around its center, around its midpoint, is given as 1/3. 1/12 ml squared, while the rotational inertia of a rod around an end is 1/3 ml squared. And then you also have the rotational inertia of a hoop is being mr squared. You have the rotational inertia of a point mass going around in a circle, which is also mr squared. And then you have stuff like a sphere, which is 2/5 mr squared. Now, for the most part, they should give you them, but these, especially these first four, are important to really know how to remember them. So put them in your calculator, write them down, do something to be able to remember these, because these come up a lot, and sometimes they don't give it to you because it's implied. Now, there are two ways to actually determine what the rotational inertia of an object is. First is using calculus by integrating calculus. Now, unfortunately, this only works for rods of uniform mass. Basically, the mass is evenly distributed along it, and the center mass would be right in the middle. All right. Now, on the reference table, you see this equation. I equals integral of r squared dm. Now, the way you go about doing this, let's say that we have a rod of mass m and length l. All right. Now, those who know calculus know that we can't integrate this equation as a function of dm because r is not in terms of dm. But both those values do change. So what I have to do is I have to change my terms, and this is how I'm going to go about doing it. I use this equation. I don't believe this is on the reference table, but you have seen this before. I mentioned that this was the linear mass density. Now, for a rod of uniform mass, this linear mass density is constant. So what we can do is we can replace this dm. We can rewrite this equation as m equals L lambda. And we could plug in this m into this equation. So we end up getting I equals integral of r squared d L lambda. Now, I just said that lambda is constant. So, as you guys know, any constant value I can pull out. So I can pull this out and bring it in front of the integral. So I end up getting this. Integral of r squared dl. And then this becomes the easy thing. I just go and is this integral of r squared is just 1/3 r cubed, and that's pretty much it. Now, the thing that's really important is at this point, I need to worry about the bounds. So what is up here and what is up here? And I'll explain that in a second. All right, so what you put in your bounds depends on the scenario that's going on. So for example, let's say I have my rod, it has a mass M, a length L, and we're doing our pivot from here, from this end. So this is x equals 0, or I should say r equals 0, and over here is r equals L. All right, and this is my pivot. So when I do my whole integral of r squared lambda dl, my bounds here, because I need bounds, I need something on the top and bottom of this integral, my bounds are going to go from 0 to L, because that's where I'm going. Starting from this side of the rod to this side, I go from r equals 0 to r equals L. Alright, so I do my whole integral again. I said before that this is 1/3 r cubed, and now my bounds are L to 0, so I end up getting lambda 1/3 L cubed minus 0. But I don't want this lambda here, I want to replace that. Remember, lambda equals m over L. Plug that in to that equation, and I end up getting m over L times the 1/3 L cubed. L, cross out with one of those, and we end up getting with this equation, 1/3 ml squared, which is exactly what we got before, the rotational inertia of a rod about one of its ends. Now, let's do another practice where instead of doing it at the end, we'll do it right in the middle. All right, so here's my rod. Pivot now is going to be right in the middle, which means that these ends, because I want to go from this end to this end, since this pivot is r equals 0, that means this end is negative L over 2, and this is L over 2. Now, if I put that on number line. Now, if I do the same exact integral, lambda r squared dl, this time my bounds are going to be negative L over 2 to L over 2, going from one end to the other end. And do my integral, get 1/3 r cubed. This time my bounds are different. Here, when I start plugging them in, I'll end up getting L cubed over 8 minus negative L cubed over 8. I just change my brackets. So lambda over 3 is, what is that, 2 L cubed over 8, which is just lambda cubed, L cubed over 12. And once again, plug in the fact that lambda equals m over L, and we end up getting, for the rotational inertia about the middle, to be ml squared over 12. Again, exactly what we got before. So this is how you use the integration form to figure out what the rotational inertia of the object is. Again, it's based off of where you are, and then you go along the entire object. Now, there is another way to do this, and that doesn't require calculus, though it does get a little bit tricky. So the other method is called the parallel axis theorem. I'm not going to explain exactly what that name means. If you're curious, you can ask me in person. Parallel axis theorem. Basically, what you're going to do here is you're going to say that the rotational inertia at any pivot is equal to the rotational inertia of the object about the center of mass. So basically, that's the rotational inertia of the object when it's rotating about its center of mass, which is always the smallest, its smallest rotational inertia. And then you add the rotational inertia of the mass about the pivot. Basically, what this means, what this means is that at that, you basically just treat the object that's rotating as a point mass going around the pivot, where the mass is located at the center of mass. Now, usually this is written out more like, so, for example, let's do another practice, because this really requires you to see the example. All right, we have our uniform rod. Let's say we're doing our pivot here, and the center of mass we know is right in the middle. This is my center of mass at half L. All right, so according to this theorem, if I do the rotational inertia at this pivot is equal to the rotational inertia of the bar about its center mass, which we already know is 1/12 ml squared, plus the rotational inertia of a mass about the pivot. Well, we know that the rotational inertia of a mass is just mr squared. So this is plus mr squared. All right, 1/2 ml squared plus, well, the center of mass is half the length away from the pivot, so this mr squared becomes ml squared over 4. All right, play around with this. We get 1/12 plus 3/4 ml squared. That's just 4/12 ml squared. And looky what we have here. The rotational inertia of the rod about its end is 1/3 ml squared. Now, the one good thing about this is that it works for any object. While the integration one, the only time you're really going to use it is for a uniform rod. This is good because it works for any object. And it doesn't matter, it could be an irregular shaped object. The one thing, though, is that unless it's a rod, you will usually be given this, unless it's a rod. All right. Another thing that kind of goes with rotational inertia and sort of similar to the parallel axis theorem is the fact that the rotational inertia of a system is just the sum of the rotational inertia of all the parts. All right. When would you see this? Good example is on the, I believe it's the APC 2008 free response number 2. It pretty much kind of acts something similar to this, where you have a beam like this, and at one end there's an additional mass placed on it. We'll call this a little mass m and this a big mass m. And they said that the rotational inertia of the rod about its center was equal to 1/12 ml squared, and they basically asked what was the rotational inertia of the system about the edge, or one of the endpoints. Well, the idea was that you want to somehow figure out what was the rotational inertia of the rod about at the end. So, rotational inertia of the rod about the end, either using the parallel axis theorem or integration. You would find that it's 1/3 ml squared. Let me make that a capital M. 1/3 ml squared. And then you would say the rotational inertia of the system is the rotational inertia of the rod around the end plus the rotational inertia of the mass around the end. So we know that the rod about the end was 1/3 ml squared, but the rotational inertia of this mass, which is a point mass, would just be a regular mr squared, where in this case the r would be equal to L as well, because it's an L distance away from the pivot. And this is what you would end up coming down with. So the three things that you need to remember about rotational inertia is: one, using the integration, and the fact that you have to combine this with that lambda equals m over L for a uniform object, uniform rod. Again, you should know how to, you need to be able to know how to do that. You have to be able to know the parallel axis theorem, that the rotational inertia around a pivot is equal to the rotational inertia about center of mass plus rotational inertia of the mass about pivot. And then the third would be that the rotational inertia of a system is just the sum of the rotational inertia of its parts. Alright, like I said, if you have any questions, feel free to ask me as soon as possible, and try some of the rotational questions that are on the AP website.